Hey everyone, welcome to our Mod 3 lecture. Today we're going to be talking about chemistry, specifically the chemical basis of life. If you've had a chemistry course before, a lot of this module might be review. If you haven't, don't worry, we're going to start from the beginning and go through the basics of chemistry and a little bit about organic chemistry and then relate all of this back to the study of biology. So starting out with a little background information. This is from the introduction to this chapter, and it's talking about coral reefs and how might a chemical compound in the air harm coral reefs. So if you don't know, coral is actually an animal. A lot of people are confused and think that it's a plant, but it's an animal. It's most closely related to jellyfish, and corals are communal organisms that build skeletons, and then the coral animals live on the outsides of those skeletons and catch prey that's filtering through the water. The chemical compound in the air that this is referring to is carbon dioxide, or CO2. You've probably heard of carbon dioxide emissions, CO2 emissions, and how they're not good for the environment. One specific reason there isn't good is due to chemistry and the effect of carbon dioxide on coral reefs. So when carbon dioxide, CO2, dissolves in water, it reacts with the water to form an acid which can disrupt the formation of coral skeletons. So the little coral organisms, the little coral animals, are no longer able to make the skeletons the correct way, and the corals end up dying. This process is called ocean acidification, and it's a pretty big threat that's facing coral reefs worldwide, and it results in coral bleaching, where you just see white coral without any of that vibrant color, which means that the coral is dead. Sometimes they can come back from bleaching. Sometimes, if the bleaching has been persistent enough, the coral is officially dead and will not come back to life. We're going to talk more about chemistry in this module, and then we'll come back to this ocean acidification example towards the end once we have a little bit more of a general understanding about chemistry. So kind of the order of this module, in this video, we're going to be talking about elements, atoms, and compounds. And then in subsequent videos, we'll cover chemical bonds and then finally water's life-supporting properties. But getting right into elements, atoms, and compounds. All organisms are composed of elements, which are usually combined into compounds. Typically, most things that are found in living things have 4 to 5 elements that make them up, sometimes more. All living organisms are composed of matter. The definition of matter is anything that has mass and takes up space. An easy way to think of mass is just weight. It's not quite the same, but for the purpose of understanding what matter is, just think of it as anything that has weight and takes up space in the environment. So a rock has matter, you and I have matter, my water bottle here, you can't see it very well, has matter. All of those things are made up of matter because they have mass and they take up space. When we look at what matter is composed of, it's composed of chemical elements, and chemical elements are the elements that you would see on a periodic table. If we actually, I'll pull up the periodic table now. There is one included in the module for this chapter, and we're going to refer back to this several times in this lecture. This is the periodic table of the elements. This is the list of all the elements that we currently know of, and that's what it's referring to when it says elements. So going back to the PowerPoint, about 25 elements on that periodic table are essential for human life. Different organisms have different requirements. I think plants only need around 19 elements to sustain life, so it depends on the type of organism. If we look at living organisms, 4 elements make up about 96% of the weight of most living organisms. Does anyone have any guesses as to what those 4 elements are? See if you can think of anything before I advance to the next slide. So if you guessed carbon, hydrogen, oxygen, and nitrogen, you would be correct, CHON. Those are the 4 most abundant ones that are in the human body. This image here shows by percentage the weight of our body of these different elements in our body. I said that a little weird. This includes water weight. So we see that oxygen makes up the most of our body weight at 65%, carbon 18.5%, hydrogen 9.5%, and then nitrogen is 3.3%. Those are the four main ones. And then below that, we have calcium, phosphorus, potassium, sulfur, sodium, chlorine, and magnesium. These are important for a lot of different things. Calcium helps the bones. Magnesium is important for nerve signals to be communicated properly. All of those have different functions and are needed. And then down here, if you notice in the tiny little tip of the big toe, we have those purple trace elements that make up less than 0.01% of our body weight, but they are super important in our body's function. And in a few slides, we'll talk about some of those trace elements and what actually can happen in your body if you do not have enough of them. But first, we're going to talk about compounds, or elements and compounds. So all organisms are composed of elements, which we just saw listed on the periodic table. A lot of times those elements are combined into what we call compounds. So a compound is a substance consisting of two or more different elements in a fixed ratio. A really common example of a compound is NaCl, sodium chloride, more commonly known as table salt. NaCl is the abbreviation for the two elements that make up the sodium chloride compound. We have Na, which is the chemical symbol for sodium. Sodium by itself is a metal. You can see here that this person has just sliced off a thin sheet of the sodium metal. And then chlorine by itself is actually a poisonous gas. But when you combine the two together, you get sodium chloride, NaCl, which is table salt and is also a solid like sodium. Another example of a compound that is really common is water. So water is made up of oxygen and hydrogen, H2O. Oxygen and hydrogen are both gases, but when you combine them together to form water, you get a liquid. So we're quickly seeing that when you combine two elements to form a compound, you can get new novel properties in the compound that aren't found in either of the elements that compose that compound. Like with water, both of the elements are gases, but when they combine together, we get a liquid. And with sodium chloride, we have a solid and a gas that combine together that form a solid that is not poisonous, unlike chlorine, and is a little bit easier to break than sodium. This is another example of emergent properties. We talked about emergent properties in module 1 when we were looking at the different hierarchical ways to examine life. We talked about how emergent properties, as you get larger, you're going to start to see emergent properties. And we use the analogy of a box of bicycle parts. If you just have a box of parts, of individual parts, it's not very helpful. But once you combine those parts into a bicycle, you now get the emergent property of having a bike that you can ride to places. And the same thing is happening here with these elements combining to form compounds, and the compounds having novel emergent properties. So this checkpoint question here is talking about what we just talked about. So explain how table salt illustrates the themes of emergent properties. See if you can just run through that briefly in your head before I pop the answer up here. So if you said something similar to the elements that make up the edible crystals of table salt, sodium and chlorine, are in pure form a metal and a poisonous gas, and they come together to form table salt, which is an emergent compound, you would be correct. So jumping back a few slides, we had that image of the human body with all the different percentages of the elements. And remember, the big toe had like 0.01% purple, and that was the amount of trace elements that by body weight in our body. We're going to talk a little bit more about trace elements now. So trace elements are common additives to food and water just to make sure we're getting enough of them, because without them, it can lead to some pretty severe health issues. So some trace elements are required to prevent disease. An example of this is iodine. Iodine If you have an iodine deficiency, if you're not getting enough iodine in your diet, it results in a condition called goiter, which is when your thyroid gland becomes enlarged. And you can see this is a woman from Burma. She has the typical symptom of goiter with that enlarged thyroid gland. Iodine is found in seafood, in leafy greens, and kelp, and sometimes dairy products. So iodine deficiency, or the prevalence of goiter, is typically found in more inland regions where iodine is not readily available in the soil. As a way to try and combat this, iodine is often added to salt nowadays. You'll see salt that is iodized, and this is to provide that necessary trace element. Sometimes, in rare cases, if someone eats a lot of highly processed foods, they can also show symptoms of goiter, and this is because the salt that is often used in those highly processed foods is not iodized, and so they may not be getting enough iodine because all the salt they're consuming is not iodized. Another common trace element deficiency is iron deficiency. It's the world's most common nutritional disorder, and it affects about 2 billion people globally. The effects of iron deficiency are really profound or pronounced in child development and like younger years. As you get to the adult age, we actually have a problem with a lot of people getting too much iron. So iron deficiency, there's a delicate balance between not enough and too much, but iron helps you move oxygen around to your whole body. So it is really important. This image here shows foods that are rich in iron, like red meats, onions. We have some legumes and beans here, raisins, eggs, leafy greens like spinach, peppers, all of those. This is cilantro over here. All of those do have iron. And iron is also added to certain foods such as cereal to help make sure that children are getting enough of that trace element in order to be able to function properly. Another interesting trace element to talk about is fluoride. So fluoride is typically added to municipal water and dental products to help reduce tooth decay. And I'm going to talk to you a little bit about a story that happened in the early 1900s and how they actually realized that fluoride helps prevent tooth decay. So many of you are probably familiar with the term fluoride. A lot of times toothpaste will say that they're fluoride toothpaste, or if you've ever been to the dentist, and especially when you were younger, they probably did fluoride treatments that they would have you sit and hold on your teeth. I remember doing them and they were not very fun, but fluoride itself is really good for your teeth and it's really beneficial to help prevent cavities. So in the early 1900s, there was a town, and I can't remember exactly where it was, but researchers noticed that everyone that lived there had really yellow, brownish stained teeth, but they had a low incidence of cavities. The stain was caused by high levels of fluoride in their water supply. And so the researchers realized that fluoride itself helps prevent cavities, and you can give it at low enough doses to not cause the yellowing or the staining of the teeth. And so after that, fluoride kind of started to be a common additive to water supplies, and we drastically saw the rate of cavities across the US decrease as we started to do this. However, some people and some groups did have a problem with this just because they didn't like the aspect that it was a public health strategy that was being forced on everyone, even though it does help reduce the rate of cavities in a population. It also, another thing to note is people who are on well water, sometimes the well water is not going to be fortified with fluoride. And so if you are on well water, it's really important to make sure that you're using a fluoride toothpaste or fluoride dental products to try and mitigate the fact that you're not getting fluoride added to the water that you're drinking, because it can result in a higher cavity rate. Several other chemicals are added to food to help preserve it, make it more nutritious, and or to make it look better. Some of them are trace elements that we need to survive. Some of them are not. We're going to talk more about food and nutrition and diet stuff in our next chapter when we talk about biomolecules, but that's kind of all we'll talk about trace elements today. A quick checkpoint question here. This one will require a little bit of math or writing it out if that if you have access to a piece of paper. So if you do have a notebook handy, go ahead and jot this down. So we have a serving of cereal that's fortified to provide 100% of the recommended daily intake, which is 18 milligrams of iron. The recommended tolerable upper intake is 45 milligrams before causing gastrointestinal upset. How many bowls of cereal can you eat before you exceed that level? So 1 bowl of cereal is 18 milligrams of iron. The max intake per day before you start to see some of those negative impacts of iron is 45 milligrams. We want to know how many bowls of cereal you can eat before you exceed that level. So this is just a simple math problem. I'm going to pull up my whiteboard here. So 1 bowl of cereal, I'm going to draw, that's our cereal bowl, equals 18 milligrams. And then the max per day is, I believe it was 45. Let me double check that. Yes, 45. So this is just, sorry for my handwriting on here. This is just a simple math problem. What we need to figure out is how many times that single bowl, 18 milligrams, will go into 45. So we're going to divide 45 by 18. You can either do that in your head or pull out a calculator, but the answer to that is going to be 2.5. And so we know that we can consume 2.5 bowls of cereal, because each bowl has 18 milligrams of iron, before we hit that max level of 45 milligrams. And we'll see if we were correct. Our answer is yes, 2.5 servings of that bowl before you exceed the 45 milligram level of iron, which can cause gastrointestinal upset, which just means an upset stomach. We're going to talk a little bit more about the actual elements on the periodic table. Each element consists of only one type of atom. You've probably heard the term atom before. It's from a word that means indivisible. So an atom is the smallest unit of matter that still retains the properties of an element. Kind of like a cell is the smallest component that is still considered alive. An atom is the smallest unit of matter that still retains the properties of an element. So if we're looking at the periodic table at carbon, an atom of carbon is the smallest unit of matter that still is going to retain the properties of carbon, not of helium or any other element. Atoms themselves consist of protons, neutrons, and electrons. These are all called subatomic particles. And also, atoms are really, really small. If you take a look at the period at the end of this sentence up here, it would take thousands of atoms to fill in, thousands if not millions of atoms to fill in that little period there. So atoms are really, really small. And they're made up of a nucleus here and then orbitals for electrons surrounding the nucleus. The 3 subatomic particles that I mentioned on the previous slide are protons, neutrons, and electrons. Again, there are over 100 subatomic particles in atoms, and if you go on to take more physics or chemistry courses, you'll probably learn about them, but there's 3 that are relevant to our discussion of elements and to biology that you really need to understand. And those are the protons, the neutrons, and the electrons. The protons and the neutrons are going to be packed into the atom's nucleus, so that central region of the atom down here. And then electrons are going to orbit the outside or orbit around the nucleus of the atom on orbitals. Protons typically have a positive charge, so they're shown with the 2 plus signs here, and they are found within the nucleus. Neutrons have no charge. You can think of the NEU as neutral, so they're no charge, neutral. They're also found within the nucleus, so I can't see my mouse. There we go. The neutrons are these 2 black dots right here. They don't have a charge. They're located in the nucleus with the protons. Electrons have a negative charge, so they're denoted by these little minus signs out here, and they form a negative cloud around the nucleus of the atom. And since they surround the nucleus, the electrons are really responsible for determining the chemical behavior of an atom and how likely it is to want to interact with other atoms. Another thing I want to note here, and we'll talk about this a little bit more, but the number of protons in an atom is going to determine what element you are dealing with. So the number of protons determines the element, and also here it says the unique number of protons is an element's atomic number. So the number of protons gives us an element's atomic number, which is going to determine which type of element we have. So I'm going to take a look at our periodic table again here. We have 2 protons in this atom. So that means our atomic number is also 2. If we take a look at our periodic table of the elements, we're going to look for the element whose atomic number is 2. The atomic number is here in the top left. And that shows us that this is helium. That atom that we were just looking at is an atom of helium because it has those 2 protons for an atomic number of 2. The electrons we already talked about, they're going to determine the atom's chemical behavior and how likely it is to interact with other atoms. And then finally, the neutrons, which don't have a charge, but they're located in the nucleus with the protons. They're going to determine something called the isotope of an atom. Don't worry too much about that term right now. In like 2 slides, we're going to go over it more. So this image here, we're still looking at, we have 2 protons, 2 positively charged protons. So we're still looking at a helium atom. This is just 2 different ways to draw it. So in this drawing here, we have the 2 protons, the 2 neutrally charged or no charged neutrons, and then the 2 negatively charged electrons orbiting the nucleus. This is an easier way to draw it to like discretely see the electrons, but this one on the right is the more accurate way to draw this because we never know exactly where those electrons are at any given point in time. So it's better to indicate where the electrons can be as this blue electron cloud, and think of this electron cloud as a realm of possibilities for where those 2 electrons are located, or an electron probability map. So this is the more accurate way to draw an atom. For simplicity's sake, in this course, when we are drawing the chemical structure of atoms, we're going to draw it in a model that looks more similar to this. And again, just to go over this one more time, in this specific atom, there are 2 positively charged, 2 protons in the nucleus, 2 neutrally charged or not charged neutrons in the nucleus, and then 2 negatively charged electrons that are orbiting the nucleus. And just to give you a sense of scale of an atom, these images are not to scale. Electrons are actually significantly smaller than protons and neutrons. So if you imagine that this whole atom here was a baseball field, let's say this whole atom is Petco Park, these protons and neutrons, the nucleus, the whole nucleus would be the size of a pea in center field, like a green little vegetable pea in center field. And then these 2 electrons that are orbiting the nucleus would be the size of little gnats buzzing around the outskirts of the stadium. So this really puts into perspective that atoms are mostly empty space, and they're kind of held together by the negative charge of the electrons and the positive charge of the protons being attracted to each other. So you've probably heard the old adage that opposites attract, and it is true. The negative charges are going to be attracted to the positive charges in the nucleus of the atom. So we talked about an atom's atomic number, which is how many protons that atom has. We haven't talked too much about the atomic symbol, but that's just the abbreviation for the element. And then we have something called a mass number or atomic mass. So an atom's mass number is going to be the sum of its protons and neutrons in the nucleus. Remember, the protons and neutrons are significantly larger than the electrons. The electrons are so small that they negligibly add to the mass of an atom, so we can just pretty much ignore them when we're calculating mass. We only need to add the sum of the protons and the neutrons. The atomic mass is going to be approximately equal to the mass number for the purposes of this course, just think of them as the same thing. So atomic mass, or the mass number, is the sum of the protons and the neutrons. We were previously looking at an atom of helium. It had those 2 positively charged protons in the nucleus, and then the 2 neutrally charged neutrons in the nucleus. We add 2 and 2 together to get 4 for the atomic mass. So I'm going to go back here. Here's our helium atom. Since I misspoke, I just want to be very clear about this. To get the atomic mass, or the mass number, we're going to add up everything in the nucleus. So we're going to add up the protons and the neutrons. So in helium, we have 1, 2 protons and 1, 2 neutrons. So 2 plus 2 gives us 4. So the mass number, or the atomic mass of helium, is going to be 4. And that's what we see here. I want to take some time now to just go over the periodic table in a bit more detail. So this is the periodic table that I provided you guys on Canvas. You've probably seen one of these before. Each one is a little bit different, but the order is going to be the same. They have a handy key up at the top here telling you what each of the numbers are. So we're looking at carbon, which has an atomic number of 6. Again, this means it has 6 protons. The number of protons is always equal to the number of electrons. So the positive and negative charges equal out. So this means that carbon has 6 protons and also 6 electrons. The chemical symbol, again, is the abbreviation for that element, so carbon. And then on this periodic table, we actually have the name of the element beneath the symbol, which is handy. The atomic weight, we just talked about that, but it's the sum of everything in the nucleus. So the sum of the protons plus the neutrons. So for carbon here, we know that it has 6 protons. We don't know how many neutrons it has, but we know that the atomic weight is 12. So we can quickly figure out how many neutrons there are in this atom by subtracting 12 minus 6. That gives us 6. So we know that there are 6 protons and then 6 neutrons because the atomic weight has to equal 12. Another thing I want you to note here, so in the top right of all of these squares is a little figure. That little figure just denotes whether the element is a solid, a liquid, or a gas at room temperature. So hydrogen, it has a cloud. That means it's a gas at room temperature. Lithium and beryllium, they have those little cubes. That means they're solids at room temperature. And then bromine over here has this drop of water. That means, you probably guessed it, it's a liquid at room temperature. A few other symbols. This purple symbol here indicates if an element is radioactive. And then if an element has a little human standing there, that means that it was artificially made. It's not naturally occurring. It was made in the lab. So like a lot of the ones with really crazy names like Rutherfordium and Dubnium, Seaborgium, all of those were created. They're man-made. They're created in the lab. Another really, really important thing to note is this line right here. Does everyone see this boulder line that extends here, down here, across here, and then it's going to go up and then kind of stair step down here. So germanium is on one side of the line, arsenic is on the other, and the stair step continues. This bold line is going to differentiate the metals from the non-metals. So the metals are anything underneath this black line, this black bold line, and the non-metals are anything outside of that black bold line. So notice here, the black bold line starts right here. Hydrogen is outside of that black bold line, indicating that it is a non-metal. And then over here, aluminum is underneath that black bold line. That indicates that it is a metal, whereas silicon is outside or on top of the black bold line. That indicates that it is a non-metal. That's going to be really important later on when we start talking about bonds that form between metals and non-metals, or metals and metals. You're actually going to be asked, if I give you a compound, you're going to have to know what type of bond holds that compound together, and the way you're going to figure that out is based on whether the component elements are 2 metals, two nonmetals or a metal and a nonmetal. So just make sure you are able to differentiate the metals, anything below this black bold line that stair steps down over here, and then the nonmetals, which are anything outside of that line, including hydrogen over here. Just keep that in mind. One last thing I want to say is over here in this far right column, we call these the noble gases, which again, if you've had chemistry before, you might have heard that term. That just means that these elements do not really readily interact with other elements. We'll talk about why in the next lecture video when we start talking about how electrons interact with the electrons of other elements. So that was just a general overview of the periodic table. We're going to go back to our lecture. The last thing I want to talk about in this video are isotopes. So remember, isotopes was mentioned previously when we were looking at the neutrons. It said that the neutrons will help you determine the isotopes of a certain element. I didn't give you the definition of isotopes then, but isotopes are going to be variations of an element that have the same number of protons, but different numbers of neutrons. Remember, it's really important that they have the same number of protons, because if they had different numbers of protons, they would be a completely different element. But they can have different numbers of neutrons in their nucleus, and this would affect the atomic mass of the element, because remember, the mass is protons plus neutrons. So if the number of neutrons changes depending on your isotope, the atomic mass of the element is going to change as well. So if we take a look at carbon here, carbon has 3 isotopes that can occur. The most common carbon, the most regularly occurring, is carbon-12. Carbon-12 has 6 protons, 6 neutrons, and 6 electrons. Make sure to note the number of protons and the number of electrons will always match. And then the number of protons for each of these isotopes, again, will stay the same, because if the number of protons was different, we would no longer be dealing with carbon. What's going to change for each of these isotopes is the number of neutrons. So carbon-12 has 6 neutrons, which gives us a mass number of 12, which is where the name carbon-12 comes from. Carbon-13 has 7 neutrons. So 6 plus 7 gives us a mass number of 13, which is again where carbon-13's name comes from. And then carbon-14 has 8 neutrons. So 6 plus 8 gives us a mass number of 14. So carbon-14 has 8 neutrons. And all of these again have the 6 electrons to match the 6 protons. Carbon-12 and 13 are normal isotopes. Carbon-14 is actually radioactive, which means that it will decay at a steady rate over time and give off radiation. This is really interesting, and it makes carbon-14 a really handy tool in studying the age of like rocks or fossils that we find in the ground. Carbon is incorporated in all living things. Carbon is pretty much included in all components of living things. And so carbon-14 helps us date and age how old something is, because we know how long it takes that radioactive isotope to decay. It has a specified half-life. Another thing I want to note is that living organisms don't discriminate between the isotopes of carbon when they take it up. It doesn't matter if it's carbon-14 or carbon-12 or carbon-13, your body is going to take up the carbon and use it the same. So this is how radioactive isotopes can be incorporated into our bodies. And like I mentioned, carbon-14 can be used for radioactive dating. There's also a lot of other uses for isotopes that we'll talk about in the next few slides, but we are going to just look at this checkpoint question. So a nitrogen atom has 7 protons, and its most common isotope has 7 neutrons. A radioactive isotope of nitrogen has 9 neutrons. What is the atomic number and the mass number of the radioactive nitrogen? So we have our normal nitrogen with 7 protons and its most common isotope with 7 neutrons. I'm going to back out of here and go to our whiteboard. I'll draw a line here. So our normal one is 7 protons and then 7 neutrons, which gives us a mass number. 7 plus 7 is 14. So this is our mass number. Our radioactive isotope, again, we know it's going to have 7 protons because it's nitrogen, but we don't know how many neutrons it will have. It has 9 neutrons. And yes, I know that you can see the answer at the bottom of that, but the purpose of this is to work it out. So just bear with me. So our radioactive version has 7 protons, 9 neutrons. If we want to figure out the mass number, it's going to be 7 plus 9. So that will give us a mass number of 16. And then it also asked what the atomic number is, I believe. The atomic number, again, is based on the number of protons, so that's going to stay the same. The atomic number will be 7, the mass number will be 16, which is what we just calculated. We're going to talk a little bit more about radioactive isotopes and their use in medicine and how they can be helpful or potentially harm us. So radioactive isotopes like carbon-14 that we just talked about are useful as tracers for monitoring the fate of atoms in living organisms. Some examples of this, scientists have used a radioactive version of CO2, carbon dioxide, to actually investigate in super fine detail the process of photosynthesis in plants and to see what exactly happens to the initial carbon dioxide that is taken up by the plants and all the different intermediary compounds it becomes before eventually the plant uses the energy of sunlight and the carbon dioxide to make glucose, which is the sugar. Other times, radioactive isotopes can be used in medicine. So like I mentioned, our bodies are going to incorporate radioactive isotopes the same as they would incorporate non-radioactive isotopes. And so if you use a radioactive isotope, you can actually then trace it in the body. They're called tracers. You can think of them as biological spies because it's really easy to find radioactive things later on. And this is what certain sophisticated imaging instruments such as PET scans, which is what is shown in this image, it's what they use. They're made to be able to detect radioactive isotopes and then create an image based on the radioactive isotopes that are detected. So an example, kind of a new use of these PET scanners is scans to detect Alzheimer's. So Alzheimer's is a condition where a lot of beta amyloid protein plaques form in someone's brain. And these plaques cause all the symptoms that you traditionally associate with Alzheimer's, such as memory loss, confusion, dementia, all of those things. They recently developed a new radioactive tracer that can bind to these plaques. And so if you give someone the radioactive tracer and then put them through a PET scan, you can see what parts of their brain light up and identify whether they're starting to develop Alzheimer's or not. These are the 2 PET brain scans of a healthy person and then an Alzheimer's patient. So you can see the healthy person, the brain is typically blue for most of these areas, which means that there's not much of the radioactive tracer detected at all. Yellow and red indicate higher levels of that radioactive tracer. And remember, the radioactive tracer is going to be binding to those beta amyloid plaques, which cause the symptoms of Alzheimer's. So in the Alzheimer's patients, we see a high incidence of those radioactive tags. So the red here indicates high radioactivity in that region. Yellow indicates moderate radioactivity. So that means that there are a lot of those beta amyloid plaques in the regions that are red and yellow. And you can see a pretty disparate difference between the healthy brain and then the brain of the Alzheimer's patient. Radioactive isotopes can also be harmful. I'm sure everyone is familiar with some nuclear meltdowns that have happened in the past, such as Chernobyl in 1986. These just serve to illustrate that there are dangers associated with using radioactive substances. Radioactivity itself is very bad for us. Like when Chernobyl melted down in 1986, a lot of the people, the first responders and the people who were there when it happened, died a few weeks later from acute radioactive poisoning. I think it was several dozen people that died within the few weeks afterwards. And then people in the surrounding area had a higher incidence of several types of cancers on down the line, even if they weren't directly there responding to the event, even if they were in the nearby area, because that radiation kind of got in the air and blew all around. So radioactive isotopes in small doses can be useful in medicine. In large doses, they're really not good. Another radioactive isotope that many people aren't familiar with is radon. Radon is a radioactive gas, and surprisingly, it's the second leading cause of lung cancer in the US after cigarette smoking. And radon is found in the bedrock in certain areas of the country, and people can actually get radon poisoning from their house. So if your house is built on bedrock that contains a lot of radon, it will gradually seep into your house and it can result in lung cancer over time. This EPA map of the US here just indicates danger zones for radon in the bedrock. Down here in San Diego, we're in yellow, which is zone 3, means low risk. Zone 2 is moderate risk, and then zone 1 in the red is high risk. So you can see the Rocky Mountain region here generally as high risk, as well as a lot of areas of the Midwest and the Appalachian Mountains over there. Just something to be aware of. And our last checkpoint question of this video, why are radioactive isotopes useful as tracers in research on the chemistry of life? We talked about a few different examples, but they allow us to see things that we otherwise wouldn't be able to see. Organisms incorporate radioactive isotopes into their molecules, and researchers can use special scanning devices to detect these isotopes in biological pathways or locations in the body, which leads to advances in medical research and just those really cool images like the ones we saw of the normal brain versus the Alzheimer's brain. So I'm going to go ahead and end this video here. We'll talk about chemical bonds in part 2 of this week's online lecture.